this video I'm going to be describing an upgraded model of the atom, something that is more suitable for us at A level. I'm going to be talking language in terms of shells, energy levels, orbitals, suborbitals, and also explaining how electrons are arranged in all of the above. So let's start by looking at the model we have from GCSE. We had the nucleus in the middle, which contained our neutrons and our protons. Our electrons were arranged in shells. We tended to call them shells. We could see the first shell could hold 2 electrons, and subsequent shells held 8 electrons. This is often called the 2-8-8 rule. The shells or energy levels we're going to keep at A level. Let me just clean this up a little. Whether you call them shell or energy level isn't actually hugely important. You might like to check your syllabus or your textbook to find out the language that your particular A-level board uses. I tend to talk in energy levels because as we go on to look at topics such as absorption emission spectroscopy, ionization energies, it makes more sense for me to describe these as energy levels. The first energy level is labelled n equals 1. Where n stands for the principal quantum number. Again, this is a descriptor that we are going to be using quite a lot at AS level and in a number of different topics. Unsurprisingly, the second energy level is n equals 2, and the third would be n equals 3, and so on. Each of these energy levels is actually made up of suborbitals, orbitals, sometimes they're called subshells, so that's what we're going to have a look at next. Each energy level contains an s orbital. Okay, so we're going to have a look at the first energy level, n equals 1. It only contains an s orbital, and an s orbital can hold 2 electrons, hence where the 2-8-8 rule came from at GCSE. So what is an orbital? An orbital is essentially a 3D space that comes from the solving of some hideously complicated equations mathematically, and they predict that the electron will be found somewhere in this 3D space. Now, what's really important to note is this is a probability, and it holds to be around about 95% true. So what does that actually mean? Well, it means that if I have an electron in my s orbital, it is most probably going to be somewhere in this space. However, there is the slightest possibility, of course, that it could be on the other side of Venus. This is just a probability, so that's worth bearing in mind, and personally I find this is where chemistry gets really, really interesting. In the centre we have got the nucleus, so you need to imagine that all of the orbitals I'm going to talk about are superimposed around the nucleus and on top of each other because they're not solid. Okay, this is just the mathematical probability of finding an electron in this particular space if it is in the s orbital. Luckily the electrons know where they're supposed to be. It all works very nicely. And we do have some evidence for this that you can get your heads around in the form of ionization energy patterns, and we're going to be looking at that in another video. Now, each of the energy levels contains an s orbital. This indicator here tells me that this particular s orbital belongs in the n equals 1 energy level or shell. This s orbital is in the n equals 2 energy level, the second energy level. As you can see, they're all spherical because they're s orbitals. If I've got an electron in my 2s orbital, it is going to be somewhere in that three-dimensional space. You'll notice that as we move up the shells, the orbitals are getting bigger. Once again, you need to try and imagine that we've got the nucleus in the centre, and these are kind of all superimposed on top of each other. If I have a think about hydrogen, for example, hydrogen has got 1 electron. That 1 electron is placed in the energy level and the orbital closest to the nucleus. we can often see them described as such or drawn as such. I've got one electron and it's in that s orbital. I draw it as a box and then an arrow or a single-headed arrow. It doesn't matter which. If we were to look at helium, He, 2 electrons, they're both in the first energy level, and we could draw them as being 2 arrows in that single box there. Why have I drawn the arrows like this? Well, electrons are negatively charged. We all know that. I would hope by now. All negatively charged. Which means that there's going to be repulsion between them. And once again, the equations predict that in order to minimize repulsion, these electrons are said to be spin paired. Okay, so this happens in order to minimize repulsion between them. And what spin paired means in terms of it for the actual electrons is that one is rotating anti-clockwise and the other is rotating clockwise on its axis. Okay, so spin pairing of electrons. Okay, let's move on to have a look at the second energy level. So we've said that the first energy level, n equals 1, the first shell, just has an s orbital. At GCSE, we said that the second shell could hold up to 8 electrons. So how does that work? Because in the second shell, n equals 2, second energy level, we have an s orbital. And we also have p orbitals. There are 3 of them. And when you solve those hideously complicated mathematical equations, it tells us that the probability of finding an electron in one of these p orbitals, that electron would be somewhere in this 3D space. You often see these drawn a bit like balloons to help you visualize that. And there are 3 p orbitals, the px, the py and the pz, and essentially these pairs of balloons are on different axes. So the x-axis, the y-axis, the z, one going up, one going back away from you, one coming towards you. One of the things that's really helpful at chemistry is if you can start to develop your ability to think in 3D. So let's have a look at boron. Okay, so boron has got 5 electrons. Of those 5 electrons, I know that the first 2 are going to be in the 1s orbital, and they are spin paired. So we're filling up our orbitals from the nucleus out. My second 2 electrons are going to be in the 2s. And there's lots of ways of drawing it. I tend to draw it like that. There are my 3 p orbitals. That's 2p. And I'm going to have an electron. My 5th electron is going to be there in the 2p. We don't need to distinguish whether it is px, py or pz. However, what we do need to know is that as we have more electrons, the p orbitals, we'd put the next electron in there and then in there before we spin paired, and this gives us the lowest possible energy by minimizing repulsion, because the electrons get an orbital each rather than being forced to cohabit, as it were. So for example, if I were to take, let's go with oxygen, 8 electrons, we've got 1s, 2s, that's 4 of the electrons, and the next 4 electrons, well, 1, 2, 3, and then the 4th one would be forced to spin pair. Often we see this written as shorthand. So for boron, I might say 1s2, 2s2, 2p1. For oxygen, 1s2, 2s2, 2p4. So when you're asked to write the electron configuration for an atom or an ion at A level, this is what we're talking about. So our first energy level, n equals 1, we had an s orbital, 1s. Our second energy level, n equals 2, had the 2s and the 2p, and altogether that allowed it to hold 8 electrons altogether. When we move up to the third energy level, if you learned it as 288 at GCSE, okay, that's not actually true. We don't go around as a habit of lying to you. As I said, we're developing models that work for what we need to explain, but after the second energy level, we get more and more electrons. The third energy level, we can hold 18 electrons altogether. We've got the s, the p, then as you can see here, d orbitals. Now, these, a bit like the px, the py, and the pz, are our sub-orbitals, and there are 5 different d orbitals. So if I have an electron in a 3d orbital, it will occupy one of these sub-orbitals. Once again, I can draw it out as a series of boxes, and each of these is at the same energy level for an atom. So it doesn't actually matter which one is the dyz or which one is the dz squared. If I've got one electron in a d orbital, I would just put it in my first box. They're all of equal energy. Now, d orbitals are absolutely crucial to explaining all of the chemistry of the transition elements. So you're going to come across this an awful lot at A2. And so to recap, I'm going to take potassium as my example. I have got my n equals 1, n equals 2, n equals 3, n equals 4. Potassium has 4 shells or energy levels. This first one consists of my s orbital, 1s, and it holds 2 electrons. My second energy level contains my 2s, which has got 2 electrons in, and my 3p suborbitals, which can hold 6 electrons altogether, hence the 8 rule. In the third energy level, we have got the 3s, again it's got 2 electrons in. We've got the 3p, which has 6 electrons in. We've just seen that the third energy has d orbitals, d orbitals, which in potassium don't have any electrons in. And then the final outer shell electron, as we described it at GCSE, is in the fourth energy level, my 4s, and that would be 4s1. Why hasn't that electron gone into the d orbital? That's a really good question. Let's have a look at that next. This is the increasing energy order of our orbitals. The 1, 2, 3, 4, 5 indicate the actual energy level. So this was the n equals 1, n equals 2, 3, 4, 5, and 6. And then within each energy level, we've got our orbitals. And within each of our set of orbitals, bar the s, there is only one s orbital, we have got our sub-orbitals. You need to learn this order. There is no other way around it. It has got to be learnt parrot fashion. 1s, 2s, 2p, 3s, 3p. Right, this is what we're looking at with potassium. Let me just change my pen here. The 4s orbital is of lower energy, very slightly, but it is of lower energy than the 3d, which is why potassium puts its outermost electron into the 4s and not into the 3d. So in terms of learning this is what we need to learn. 1s, 2s, 2p, 3s, 3p, 4s, 3d. And then we can follow it up. 4p, 5s, 4d, and you won't ever have to go any further than that. Okay, so but you need to learn this, and you need to learn how many electrons we can get into each type of orbital. So to recap, 2 in an s orbital, up to 6 in my p orbitals, because I've got 3 sub-orbitals. For the p orbitals, you should, if one were honest, be able to draw them out. It doesn't have to be any more exciting than this. And often these are called lobes. So you might see that terminology there, but you need to be able to draw them out, and you can label them as, so that would be Py, that would be Pz, and that would be Px in the way that I've drawn them. And then we need to know that we've got 10 electrons in our d orbitals. You need to know that there are 5 of them. You'll be noticing here that each suborbital can only hold 2 electrons, regardless of which energy level it's in. You don't need to be able to name or draw out your d suborbitals. They're getting quite complicated. So a typical exam question might ask you to write out the electron configuration for carbon or neon or chlorine or titanium, the ones that I have here. So carbon has 6 electrons, and just working up the scale, 1s2, 2s2, 2p2. Neon, with its 10 electrons, 1s2, 2s2, 2p6. Chlorine, 17 electrons, 1s2, 2s2, 2p6, 3s2, 3p5. Titanium's a transition metal. Transition metals, remember we're filling the 4s before the 3d. So we have got our 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2. Okay, let's be clear here. You should write it numerically, even though we fill the 4s before we fill the 3d. Okay, so we're filling our s orbitals, 4s, before we fill our 3d. Is there a quicker way of writing it? Yes, there is, luckily. What you will notice here, here's my electron configuration for neon. Chlorine, the first part of its electron configuration is the same as neon. So we can write neon 3s2, 3p5. So on the periodic table, we're just going back to the noble gas before element, using that in square brackets, and then the bit that's left over. Often we are asked to work out the electron configuration for an ion. We do it in exactly the same way. So a sodium atom has 11 electrons, but a sodium ion has 10 electrons. So it is going to have the same electron configuration as neon, 1s2, 2s2, 2p6. And the same for an oxide ion, 2 minus, with once again oxygen atom has 8 electrons, the oxide ion therefore has 10 electrons because we've added 2, and it's going to have exactly the same electron configuration, 1s2, 2s2, 2p6. Okay, so it would be absolutely no fun whatsoever if all atoms obeyed the rules, and there are a couple of transition metals that we need to know about that break the rules. We're going to have a look at chromium, which has 24 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s, 1. Well, that's unusual. We would expect it to be 4s2, 3d4. It hasn't filled its s orbital, even though it's of lower energy before it's 3d. Why might that be? Let's have a look here. If I were to draw out my suborbitals for the 3d5 and the 4s2, hopefully we can see that by arranging it like so, 3d5, 4s1, each electron gets its own suborbital. If we actually followed the rules, my eraser is a little bit too big there. Let's draw my box back on. We would have 4s2, 3d4, where we've got two electrons here spin paired and then an empty suborbital. Now clearly it is more stable or of lower energy for chromium to fill each of its d orbitals and just put one electron in its 4s than the other way round. Copper is also in exactly the same bracket. So copper is 29, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. And for exactly the same reason. It is of lower energy, more stable for the copper atom to spin pair each of the d suborbitals in the third energy level than to go for 4s2, 3d9. You just need to learn this. The other thing that we need to be clear about with transition metals is that when they form ions, they lose their 4s electrons before the 3d. Okay, so they fill the 4s before the 3d, which makes sense because 4s is generally of lower energy than 3d. But when we're forming ions and losing electrons, it's the 4s that we lose before the 3d, even though they are technically of lower energy. And some of the reasons surrounding that will become clearer when you look at transition metal chemistry in a little bit more detail. So, for example, if I've got a chromium 3 plus ion, I've essentially got 21 electrons, we've lost 3, and we end up being, I'm just going to do the last bit, 3s2, 3p6, 3d3. It has lost this electron first, and then it lost 2 of its d electrons. And that is the same idea for all transition metals. It would lose their 4s2 for the majority of them before they lost their 3d. Okay, and let's finish off by very quickly pulling this back to have a look at the pattern of electron configuration across the periodic table. We've got groups running vertically, and we have the periods that run horizontally. Now, one of the reasons that I like to call these energy levels is if we have a look here, we can see that each period is actually about the number of energy levels that that atom has. So for potassium we saw, for example, potassium in 4 energy levels and n equals 4, and it's in period 4. Sodium, 3 energy levels, n equals 3 being the energy level that its final electron is in, and it's in the 3rd period. Sometimes you might see that these are described as the S block, the D block, and the P block. And that comes from the idea that, for example, in the P block, each of these elements is putting its final, its last, its outermost electrons into p orbitals. So if we have a look at fluorine, for example, it's got 9 electrons, 1s2, 2s2, 2p5 its final electrons are going into p orbitals, therefore it is in what we call the p block. I want to compare that with chlorine. I'm going to move on down here. Okay. Chlorine has 17 electrons, so we can, in shorthand, neon, and then we have 3s2, 3p5. The 3 corresponds to chlorine being in the third period. It's filling up electrons going into its third energy level. But if you will notice, and this is the point I'm trying to make here, the final electron configuration is identical for elements that are in the same group. Now, there is a reason why I am bashing on about this, because there is a nasty trick that examiners play where they might say, for example, what is the electron configuration of iodine with its 53 electrons? And people slowly work through trying to remember the order, and then they get to the point where they can't remember what happens after the 4s, understandably. They get in a bit of a panic because they were told not to learn any further, and we've got 53 electrons, and they just start making it up. It's a trick question, because all we need to do is look at elements higher up in the same group. I can see that iodine is in group 5, and I can see that the noble gas before it is krypton. So I can quite simply say it's going to be krypton, 5s2, 5p5, because it's following exactly the same pattern as the other elements in that group. And that is going to hold for any question that they ask you. So if we know carbon, we can work out lead, for example, without having to worry about the order of all the electrons and the orbitals and the suborbitals that go in between the ones that we know, up to maybe 4s, and the ones that are happening in the 6th energy level. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the description below, it'll take you straight to Crunch Chemistry School, where you can access my free maths skills course, complete tuition, and worksheets designed specifically to build your confidence and stretch you. Together we can do this.